Okay, so welcome back to another video. Here's a nice little functional equation that we would like to solve. So we want to find all functions f that map from the positive rational numbers to the codomain range of the positive rational numbers that satisfy these following two conditions. We have that f of x plus f of 1 divided by x equals 1, and then f of 1 plus 2x is equal to 1/2 times f of x. So just like your standard, the way you usually solve functional equations itself is usually like to check its own base case. So try to choose one of the simpler solutions for a value x to actually get a baseline on how the function is structured to the point that we can actually utilize a bunch of, solving in a way of doing systems of equations that we'll be utilizing as a way of using it as a hint. So utilizing that, and then once we actually get to the equation that we actually find the general solution based on those observations, we actually would like to verify such that it actually does satisfy those two functions over there. So basically nothing much needs to be said, as this is basically just like an easier standard case of finding solving functional equations to that extent. So why don't we just jump right in. So first thing, let's actually plug x equals 1 into our first equation over here. So that means I have f of 1 and then plus f of 1 divided by 1 is then equal to 1. This implies that we have f of 1 plus f of 1, aka 2 times f of 1 equals 1. So we can actually come to the deduction to say that f of 1 is equal to 1/2. So I'll just label this equation number 1 because that'll come in handy. So let's plug x equals 1/2 into our second equation. So that means I have f of 1 plus 2 times 1/2, and then set that equal to 1/2 times f of 1/2. Okay, and so we actually just solve this out. So we have 1 plus 2 times 1/2, so it's pretty much just f of 2, so is equal to just 1/2 of f of 1/2. So f of 2 is equal to 1/2 times f of 1/2. I'll just label this equation number 2. Okay, so now let's plug x equals 2 and x equals 1/2 to the first equation. So let's actually go to a different marker for this one. So now plug x equals 2 to the first equation. So now that'll just lead us with f of 2, and then add this with f of 1/2. F of 1/2, and then set that equal to 1. When we call this equation number 3. And so we plug, now as mentioned, let's plug x equals 1/2 to the first equation as well. So then that would mean we have f of 1/2, and then add this with f of 1 divided by 1/2, which is just f of 2. So then that just sets the equal to just number 1. So we call that equation 4. Okay, so we have 4 equations that we're dealing with. So we have, the values if we want to call it to that extent. F of 1 equals 1/2, f of 2 equals 1/2 times f of 1/2, f of 2 plus f of 1/2 equals 1, and then f of 1/2 plus f of 2 is equal to 1. Okay, so what we can do here is let's substitute equation number 2 back to equation number 3, since we have something for f of 2 that we can substitute back into. So let me actually write sub equation 2 to equation 3. So then that just leaves us with f of 2, so f 1/2 then times f of 1/2, and then add this with f of 1/2 is then equal to 1. So we can further imply that this is going to be 3 over 2 times f of 1/2 is then just equal to 1. And then we can solve that f of 1/2 is then just equal to 2 divided by 3. Okay, now if we just go back to equation number 2, so because we just solved something for f of 1/2. So going back to equation number 2, we have that f of 2 is then just equal to f of 1/2 times f of 1/2, which of course we solve for what f of 1/2 is, so that means it's just 1/2 times 2 divided by 3. So that'll just imply that we have that this is equal to, 1 over 3. Okay, so now we got so basically we have 3 values we got. So we have that f of 1 is equal to 1/2, then f of 1/2 is equal to 2 over 3, and then f of 2 is equal to 1 divided by 3. Hang on, let me fix that. So now, if we actually just make the observation based on these three values, we can actually come to a generalization to say that f of x is equal to 1 divided by 1 plus x. So we're not done yet. So now what we need to do is let's actually check that it satisfies the two equation. So we have f of x equals 1 divided by 1 plus x. So let's plug that back into here. So now, okay, let me actually now go to a different marker for this one. So first equation we have that it says f of x plus f of 1 divided by x is equal to 1. So let's check that. So I have 1 divided by 1 plus x, and then plus 1 divided by 1 plus 1 divided by x. So if we actually just simplify it down, so that means I have 1 divided by 1 plus x. I'll just multiply x to the numerator and denominator. So I have x divided by 1 plus x plus 1, it's commutative. So therefore, combine everything together since it's got the same common denominator. 1 divided by 1 plus x divided by 1 plus x is then equal to 1. So that checks out. Okay, so now let's actually go into the second equation to verify. So we have f of 1 plus 2x is equal to 1/2 and then f of x. Okay, plug that in. So I have that this is going to be 1 divided by 1 plus in the quantity 1 plus 2x. So then that sets that's going to equal to just 1 divided by 2 plus 2x, which of course I can factor out the 2. So it's just 1 divided by 2 times 1 plus x. Okay, then I can factor out that 1/2. So it's 1/2 multiplied by 1 divided by 1 plus x, but the 1 plus x is of course that f of x, which is verifies that's 1/2 times f of x, which of course that checks out. So it does satisfy our two conditions. So therefore that means our only unique function is that f of x is equal to just 1 divided by 1 plus x that satisfy these two equations over here. And of course, you can actually utilize for all the rational functions, the positive rational numbers rather, to see and verify that it does indeed match up with these two. Just like that very, very simple case of just making the observations of plugging in values, and then if we come to a generalized, observation conclusion to, of course, then afterwards verify that it actually does check out for these two equations to come to simply just this. So yeah, that's pretty cool if you ask me.